Greetings, everyone, and welcome to the Pan Future Society podcast, episode number 29. Today is Friday, December 9th, 2016, and this week you probably heard that astronaut Congressman John Glenn passed away, and that is sad news. He was the first American in space with the Mercury project, and also the last surviving astronaut of the Mercury 7. So there's tons of news out there to fill you in all about John Glenn's fascinating career and life, so I don't need to rehash that there. I'm sure you can find it just about anywhere you look. But there is another space exploration related bit I wanted to throw at you at the start of the show this week. Why do we try? Why do we go to unknown and dangerous places? David Simmons was an American physician and in the U.S. Air Force, and he was part of Project Manhigh, which in the post-World War II era was an early attempt at exploring the edge of space and figuring out the effects that being outside the atmosphere or very, very high in the atmosphere might have on people. Project Manhigh used balloons to carry capsules high up into the atmosphere, and for Manhigh 2, Simmons flew this balloon 19 miles above the planet before then jumping out and parachuting back to Earth. And one thing that he did while he was up there was that he took a chart of paint colors with him. They were trying to nail down the color of the tint of the upper atmosphere, which X-plane pilots had mentioned was a very odd color. Well, it turns out the color wasn't on the chart. And of this, he said, where the atmosphere merged with the colorless blackness of space, the sky was so heavily saturated with this blue-purple color that it was inescapable. Yet its intensity was so low that it was hard to comprehend, like a musical note, which is beautifully vibrant, but so high that it lies almost beyond the ear's ability to hear, leaving you certain of its brilliance, but unsure whether you actually heard it or dreamed of its beauty. That's why we go. Scientific endeavors push our technology and knowledge of the universe, and yet can be deeply spiritual experiences. It's not just about the fastest rockets or fanciest gadgets, it's about continuing to advance and enhance the human experience in the universe. Now on to your news of the moment. Some medical news for you this week. Some researchers from Harvard, the EMPA Research Group, and the Adolf Merkel Institute have come up with a way to possibly fight against sepsis. Sepsis is an infection of the blood that infiltrates the whole body and is quite often fatal. Treatments are massive doses of antibiotics, and there's always a concern that the bacteria could become or be resistant to any antibiotics, and then you're just out of luck. These researchers have used a new way of treating sepsis, possibly with magnets. They coated antibodies that would bind with a particular bacteria with iron particles, and then introduced the sepsis-causing bacteria to the antibodies in a solution. These antibodies latched onto the bacteria, and that solution was run through a dialysis machine, and magnets pulled the iron-coated antibodies and bacteria out of the solution. One downside to overcome from this off the top is that the antibodies can only attach to one type of bacteria, so you either have to generate them for each type or come up with a way that this could be generalized. And of course, this is a very early thing. This is done in a lab in a petri dish in some tubes. Has not been done in a person, let alone any sort of animal testing or anything like that. However, this adds one more potential tool in our arsenal against bacteria, which is continuing and probably will always be something for us to deal with as more and more things become resistant to antibiotics, or as climate change possibly even releases some things from permafrost that we haven't faced in a long time. We're going to need all the tools we can get. And now, it came from outer space. In your space news this week, NASA's Cassini spacecraft has sent us some brand new photos from the beginning phases of its new mission. It has changed its orbit to swing high above the northern hemisphere and then skim past the outer edges of the planet's rings. And we don't have photos of the rings yet, but we do have some new photos of the northern hemisphere and the North Pole. Some really great shots of the atmosphere and weather that goes on Saturn, and of the oddball hexagon shape that is at the North Pole there. So I will link to this in the show. Go check out these new pictures from Cassini, and keep your eyes peeled. I suspect very soon we will be getting more pictures, maybe some close-ups of Saturn's rings. And this is the last mission in detail for the Cassini probe before it will be plunged into the planet. Cassini was launched in 1997 and has been in orbit since 2004. So it has sent us a lot of information about Saturn and its moons. And in case you were wondering why they would crash it into the planet, aside from getting one last little bit of data, one of the decisions to do this, they're doing it with Cassini, they've done it with other probes at Jupiter, I believe, and it is to make sure that they don't potentially crash into one of the moons. And because these gas giants have some interesting moons that have liquid water and seas of methane and very other interesting phenomena that could harbor life, or could just be very interesting, and we don't want to crash our junk into the moons. So slinging it into the planet with its huge size and gravity, we're going to hardly make a dent in it, but we'll get some interesting data before it dies. So Cassini, check that out. I will put the link in the notes. And that's it for your news of the week. Continuing on the topic from the last couple of shows on threats from outer space. Asteroids and comets are not the only events in space that can threaten our world. Some, like a gamma ray burst aimed at us just right from a distant supernova, would be exceedingly unlikely, hard to predict, and there's really nothing we can do about those. A GRB is a possible explanation for the Ordovician-Silurian mass extinction 450 million years ago. Closer to home, and much more frequent and even predictable, at least by observing sunspot activity, solar flares and coronal mass ejections from our own home star can be a significant threat to our planet. Unlike GRBs, we can actually do quite a bit in the event of a significant solar flare striking the planet. First, let's define solar flares and coronal mass ejection. A solar flare is a burst of energy released from the sun in relation to magnetic energy and sunspots. Flares are difficult and sometimes impossible to see with the naked eye. Public service announcement required here: don't ever look directly at the sun for any reason without proper equipment. That is the end of your PSA for today. Many of the videos and images of flares that you'll see online are recorded in the X-ray and ultraviolet spectrums, though flares release a huge amount of energy across the entire spectrum from radio waves to UV. These flares can release up to 1 times 10 to the 25th power joules of energy, roughly equivalent to 1 billion tons of TNT. The flare jets out clouds of electrons, ions, and atoms into space. These jets of material usually take 1 to 2 days to reach the Earth. In addition to making for some spectacular auroras, all of this energy entering the atmosphere can be disruptive to electrical devices and also poses a threat to satellites and any astronauts aboard the International Space Station or otherwise in orbit. A solar prominence is a loop of material on the sun's surface bound by strong magnetic energy. On these lines, plasma will form and flow along the loop. When one of these loops snaps, it produces a coronal mass ejection. CMEs often but do not always go hand in hand with solar flares. This blast can carry billions of tons of matter into space and put it on a collision course with the Earth. One result is a geomagnetic storm, where Earth's magnetosphere undergoes severe disturbance. Among the threats to any astronauts in space is the possibility that they would receive a career allowable radiation exposure in just a few hours, and an event severe enough could be life-threatening. Related to and sometimes being caused by the above also are solar proton events and EMPs, electromagnetic pulses like those associated with nuclear weapons. Like asteroids, flares and CMEs are events that have happened and will happen again. So far, we've just been fairly lucky not to be bullseyed by a big one in recent history. When all this energy collides with our magnetosphere, it is conducted along those lines of electromagnetic energy, like the ground wire for your house. If enough energy hits us, it can be carried all the way to the ground, as well as pushing farther south or north away from the poles. This is why auroras reach points far beyond normal sometimes. Much of the potential damage comes from power grids and electrical power devices getting a sudden overload power surge. The Carrington event of 1859 was a large flare, named after astronomer Richard Carrington, who, independently with Richard Hodgson, made the first observations of the flare. In 1859, there wasn't much electricity in use, but it did have a great impact on telegraph lines. Systems in Europe and North America failed, some operators got electric shocks, and other operators continued sending and receiving messages even after disconnecting their power sources, as there was so much energy being channeled into the lines. Stories from that time also report that people in the northeast U.S. could read newspapers by the aurora light, and the auroras were visible as far away from the poles as Senegal, Liberia, Cuba, and Hawaii. It has been estimated that a similar event today would cause between $0.6 and $2.6 trillion in losses in the U.S. economy alone. A more recent event in 1989 knocked out a power grid in Ontario, Canada, pretty much across the entire country. Many millions of people were without power, and it took a while to get them all back online. This one I actually remember seeing when I was much younger. I did see quite spectacular aurora at my house where I was living in southeastern Wisconsin. The latitude there is, I think, about 40 or 41 degrees north. So that is quite a bit farther south than auroras usually go. Occasionally they do, but at the time it also did some damage. So, among the consequences of an event like this, as I had mentioned, the threats to astronauts, to satellites receiving a large power overload, to the power grids themselves receiving a large overload. Um, there are also threats to navigation and aviation communication. For one thing, GPS satellites could be knocked out, and also flights that go over the poles, because it is a shorter route, uh, go out of range of GPS satellites when they do so, so they use high frequency radio to stay in communication with the ground. But however, during a large solar event like this, that radio communication would also be disrupted, and in the past, flights over the poles have been redirected farther south. Believe it or not, oil pipelines can be disrupted by these events as well. That much energy flowing into the ground apparently can cause inaccurate readings in the flow rate and pressure sensors of the pipelines. And then, if you have bad readings, you might make an adjustment to the flow in the pipe that is incorrect. So, there is actually such a thing as space weather. That is part of what NASA and other space agencies do. They monitor these things going on, and this information is then shared with organizations like the FAA, the Federal Aviation Administration, and pipeline operators. In the event that something is going to happen, hopefully we get enough notice and they can do things to prepare. So think about how much we rely on electricity. Are you ready to cope without power for a few days or even a few weeks? Some of these events, these large events that happen to the power grid, even some of the outages, like the 2003 one in the Northeast that hit New York and other states out there and parts of Canada, millions of people were without power, and some places in some rural areas, it took weeks to get power back to those people. More than just not being able to use Google Maps, a loss of satellites would interrupt large parts of the economy. Many of the seemingly instant credit card transactions that you make are enabled by satellite transmission from the store to your bank as well. Some have speculated that a very catastrophic type of event could put power out in places for months. I did read a few things. It was a bit of a hyperbole from the Daily Mail, not necessarily something scientific. But in the power grid, the transformers are what's most affected by these surges, and they get knocked out. And at large stations and substations, these transformers aren't something that you can just pick up off the shelf when you need a new one. If there is a large outage and it takes out a lot of transformers, it could take a very long time to get replacements in place. So there is some concern that an event would last longer than a few weeks. But we aren't totally out of luck. In an immediate sense, the best option is to turn things off so they're not running when power surges occur. I think most, if not all, satellites have safe modes, and things like power grids can be temporarily shut down. An inconvenience for most, but it could save us from having outages due to blown transformers that could last days or weeks. Going forward, there are ways to build satellites and other craft with more protections. We also need to invest in the power grid. At least in the United States, we have an aging grid that can be easily prone to problems even without an event from outer space. Better, newer technology, more localized grids, and diversification in energy production can all lessen the impact of a flare or coronal mass ejection. There are a number of space-based observatories run by NASA and others that keep an eye on the sun and alert us to any changes or events like flares and CMEs. In Carrington's day, you might have noticed a flare only if you were looking at it at the time. Now we can keep a round-the-clock watch, and these programs must be supported. If seen right away, we could have a day or two, or perhaps only an hour or two, to try to mitigate the effects of a solar event. This is another aspect of long-term thinking that can be difficult, sustaining effort and vigilance over a long period of time. When you're swinging the political pendulum back and forth 2 or 3 times per decade, the importance of keeping a watch for threats that are rare can get lost in the shuffle. No matter who holds political power, there are some things that transcend the pointless borders we draw on maps. All right, that is your show for this week. Thank you once again, everyone, for joining me. And thank you so much for sticking with me over these months that I've been doing this podcast. The service I use to host the audio files gives me some statistics about how many downloads and whatnot there are. And in combination with the YouTube plays, I've hit about 2,300 downloads at this point, and that is really cool. It's a tiny drop in the bucket of podcasting, as some of the podcasts I listen to, I have heard get 20,000 downloads a week. So I've got a long way to go, but to hit 2,000 in less than 30 episodes, and since I've only been doing this since the end of May, it's really cool, and thank you for listening, because I do this to share information with you, to share sometimes my opinions with you. Whether you agree or disagree, let me know. That's what I'm here for, to have a conversation. This can certainly be a two-way street, so if you would like to drop me a message at sean@panfuture.org, or swing by the Facebook page or find me on Twitter, you can get in touch with me that way, and it will all be good. And I will talk to you again in the future.